This is Heliox, where evidence meets empathy. Independent, moderated, timely, deep, gentle, clinical, global, and community conversations about things that matter. Breathe easy. We go deep and lightly surface the big ideas.
Hey everyone, welcome back to another deep dive. Today, we are going to try to tackle something that sounds like it's straight out of science fiction.
Oh, yeah.
Time crystals.
Definitely.
You sent over some research on a recent breakthrough, and honestly, when I saw the term topologically ordered time crystal, my brain kind of did a backflip.
Yeah, I admit it's a mouthful even for those of us
Yeah.
in the field.
Yeah.
But it's a fascinating concept, I promise.
Okay, so before we even get to the topologically ordered part, let's start with the basics.
Sure.
What exactly is a time crystal? Is it like some kind of magical gem that controls the flow of time?
Not quite.
Okay.
Although the name is definitely catchy. Think of it this way.
Yeah.
Imagine a pendulum that just keeps swinging forever
Oh.
without ever needing a push.
Mhm.
It never slows down or loses energy.
Okay.
That's kind of what a time crystal does,
Uh-huh.
at least at the atomic level.
So it's like defying the laws of physics where things tend to settle down over time. Yes. In physics, we talk about systems reaching their lowest energy state, their ground state,
Right.
where they become stable and stop moving.
Right.
But a time crystal is different.
Okay.
It keeps oscillating or changing,
Mm-hmm.
even in its ground state, breaking what we call time translation symmetry.
Okay, so instead of just sitting still, it's always in motion, even at its lowest energy level?
Right.
That already sounds pretty bizarre, but how does that even work?
It's because the atoms in a time crystal are arranged in a very specific way
Okay.
that allows them to keep moving without any external force.
Okay.
They're like tiny dancers in a perfectly choreographed routine,
I like that.
constantly switching places and interacting with each other.
That's a great way to visualize it. So it's not like a perpetual motion machine that
Right.
violates the laws of thermodynamics.
Right. It's not creating energy out of nothing.
Okay.
It's more about how the energy within the system is organized and distributed,
Okay.
leading to this persistent rhythmic behavior.
Mm-hmm. Okay, so we have this mind-blowing concept of a time crystal, something that never stops moving even at its lowest energy state.
Right.
But what about the topologically ordered part?
Yeah.
What does that even mean?
This is where things get even more interesting.
Okay.
To understand topological order,
Yeah.
let's think about a donut and a coffee mug.
Okay.
They look different, but they both have one hole, right?
Yeah, I see where you're going with this.
Topologically, they're the same.
Okay.
It's about the fundamental properties that remain unchanged,
Uh-huh.
even if you stretch or deform the object.
So topological order is about looking beyond the surface and seeing those underlying unchanging characteristics.
Exactly. Now apply that to our time crystal.
Okay.
The way its atoms are arranged gives it a specific topological order.
Okay.
And this means that its time crystal behavior, that constant oscillation,
Right.
is directly tied to this underlying topology.
Okay, I'm starting to get it. So it's not just any random oscillation, it's an oscillation that's deeply connected to the structure of the time crystal itself.
Right. And this has some mind-bending implications.
Yeah.
Because of this topological order, you can't directly observe the time crystal's oscillations
Okay.
just by looking at individual atoms.
Okay.
You have to look at the system in a very specific, non-local way to see it.
Wait, non-local? So it's like trying to understand a dance just by watching the shadows of the dancers, not the dancers themselves?
That's a great analogy. You're getting the idea.
Okay.
We'll dive deeper into what non-local measurements mean in a bit. But first, I think it's time to address the big question.
Okay.
How did scientists actually create this elusive thing?
Yeah.
How do you even make a time crystal, let alone one that's topologically ordered?
Right, because this all sounds incredibly theoretical.
Yeah.
Did they find a time crystal hidden in a cave somewhere? Or did they build it in a lab?
No caves involved. They built it
Okay.
on a quantum computer, which is kind of fitting given the mind-bending nature of time crystals.
All right, this is where I think we need to make sure everyone's on board, because quantum computers are a whole other level of complex.
Absolutely.
We'll pick up right here in the next part.
Sounds good. Thank you to everyone who has left such positive reviews on our podcast episodes. It helps to make the podcast visible to so many more people. We read them all. Back to Heliox, where evidence meets empathy.
Okay, so we're back, and we've established that time crystals are real, they're bizarre, And they were created using a quantum computer.
Right.
I have to admit that last part makes my head spin a little.
Yeah.
Can you help us understand how they actually did that?
Absolutely.
Yeah.
To create this time crystal, the scientists used a special kind of quantum computer with components called qubits. Think of qubits like the bits in a regular computer.
Okay.
But with a quantum quist,
Okay.
they can exist in multiple states at the same time,
Okay.
allowing for much more complex calculations.
Okay, so instead of just being a 0 or a 1, Gary, a qubit can be both at the same time. That's some serious multitasking.
Exactly. Now, in this experiment, they arranged 18 of these qubits
Okay.
in a specific way to mimic a system that theoretically could host a time crystal. It's like setting up a tiny, carefully controlled quantum playground.
So it's not like they found a naturally occurring time crystal.
Right.
They had to build the right environment for it to exist.
Precisely. They used a quantum computer to simulate the conditions needed for a time crystal to emerge.
I'm trying to imagine what that looks like. Are we talking about physical qubits, like tiny particles or something?
In this case, the qubits were made using superconducting circuits.
Okay.
Think of them like microscopic loops of wire, cooled down to extremely low temperatures where they exhibit quantum properties.
Wow.
These superconducting qubits can be manipulated with incredible precision
Okay.
using microwaves and other techniques.
So they're using these super cooled wires to create a system that can behave like a time crystal. That's pretty wild. But how do they actually get the qubits to do what they want? How do they, program the quantum computer to make a time crystal?
That's where things get really tricky. They had to design a specific set of instructions, a quantum circuit that would make the qubits interact in just the right way to simulate the conditions needed for a time crystal. They actually used a special algorithm called a neuroevolution algorithm to help design the best possible circuit.
A neuroevolution algorithm? That sounds like something straight out of a sci-fi movie.
It's a pretty cool technique. They basically trained an AI to find the most efficient way to manipulate the qubits to get the desired time crystal behavior.
So it's like teaching a computer to choreograph the perfect quantum dance for these qubits to perform?
Exactly. And the complexity of that dance is mind-boggling.
Yeah.
They had to account for interactions between multiple qubits simultaneously.
Wow.
Which is incredibly challenging even for a quantum computer.
Okay, so we have the stage set a quantum computer with 18 superconducting qubits.
Right.
All programmed with this incredibly complex quantum circuit.
Yes.
What happens next? How do they know if they've actually created a time crystal?
Now comes the exciting part, observation. Remember the hallmark of a time crystal?
Yes.
Is that it breaks time translation symmetry.
Right.
Meaning it keeps oscillating even in its lowest energy state.
Right.
So they had to look for signs of that symmetry breaking in their measurements.
So they're looking for evidence that the system is ticking like a clock, even when it should be at rest. But how do you even observe something happening at the quantum level?
It's not as simple as just looking at the qubits under a microscope. They had to use very specific measurement techniques, what we call non-local measurements, to probe the collective behavior of the qubits.
Can you give us a more concrete example of what a non-local measurement means?
Imagine you have a row of light bulbs.
Okay.
But you can't see the individual bulbs directly.
Okay.
You can only see their combined brightness.
Okay.
A non-local measurement would be like observing the overall brightness of the row to infer what's happening with the individual bulbs, even though you can't see them directly.
Okay, that makes sense. So they're not looking at each qubit individually, but rather at the overall pattern of behavior across all the qubits.
Exactly. And when they did this, they found something truly remarkable. The system was oscillating with a period that was twice as long as the period of the driving force they applied to it. Think of it like pushing a swing. Every other time, it reaches its highest point. And still seeing it swing back and forth regularly.
Wow.
This is that subharmonic response we mentioned earlier, and it's a clear signature of time translation symmetry breaking.
So even though they were only nudging the system every other beat, it was still oscillating at its own steady rhythm. That's a pretty convincing sign that they'd created a time crystal, right?
It was a major piece of the puzzle, but they didn't stop there to further confirm that they were dealing with a topologically ordered time crystal. They had to look for another signature, something called entanglement entropy.
Okay, that's another one of those terms that makes my brain hurt a little.
Right.
Can you break it down for us?
In simple terms, entanglement entropy is a way to measure how much the different parts of a quantum system are interconnected. In a topologically ordered system like our time crystal,
Okay.
you expect to see a high degree of entanglement, meaning the qubits are all deeply linked together in a very specific way.
So it's like measuring how much the dancers in our quantum choreography are intertwined with each other.
A perfect analogy.
Yeah.
And when they measured the entanglement entropy in their system, it matched the theoretical predictions for a topologically ordered time crystal. So that was another big check mark in their favor.
All right, so we have these two key pieces of evidence, the subharmonic response and the high entanglement entropy.
Right.
That seems pretty conclusive, right? They actually created a topologically ordered time crystal.
Yes. It was a groundbreaking achievement, and it opened up a whole new world of possibilities for exploring the bizarre and fascinating realm of quantum time crystals.
This is all incredibly mind-blowing. We've gone from a seemingly impossible concept.
Right. To a real tangible experiment.
Yeah.
With concrete results.
Yeah.
But I'm sure you're not done yet. There's more to this story, right?
There's always more to explore. They didn't just create a time crystal and call it a day.
Right.
They wanted to understand its properties,
Sure.
its limitations, and its potential. And that's where things get really exciting.
Okay, I'm on the edge of my seat. What do they do next?
Well, remember how we talked about the robustness of topological systems, how they can withstand certain disturbances?
Yeah.
They wanted to put that to the test.
So they tried to break their time crystal.
In a way, yes. They introduced small perturbations,
Okay.
controlled disturbances, to see how the time crystal would respond. Think of it like gently shaking the quantum playground.
Yeah.
To see if the time crystal could keep ticking.
I love that analogy. So what happened? Did the time crystal survive the shaking? Well, they found that for small disturbances, the time crystal held strong. It kept oscillating, showing that it has a certain level of resilience built in thanks to its topological nature.
That's impressive. It's like a quantum version of those inflatable punching clowns. You can knock it down, but it keeps bouncing back.
I like the way you think. But of course, there's a limit to how much any system can withstand when they increase the strength of the disturbances.
Yeah.
The time crystal eventually lost its unique properties and behaved like an ordinary quantum system.
So they found its breaking point, the point where its quantum weirdness gives way to more predictable behavior. I guess that makes sense. Even the toughest materials have their limits, right?
Absolutely. And knowing those limits is crucial for understanding how to potentially use time crystals for practical applications.
Okay, so we've gone through the whole story, what time crystals are, how they were tested, and how they proved to be surprisingly resilient. It's been quite a journey, but I still keep coming back to the so what question. Why should we care about time crystals? What makes this discovery so important?
That's the key question, right? It's not just about the cool factor, although that's certainly there. Time crystals could have a significant impact on fields like quantum computing.
Ah, yes, quantum computers. We touched on that earlier.
Right.
But can you remind us why this is such a big deal?
Imagine a computer that can perform calculations millions of times faster than the best computers we have today. That's the promise of quantum computers.
Okay.
They have the potential to revolutionize everything from medicine and material science to artificial intelligence and cryptography.
So we're talking about solving problems that are currently impossible even with supercomputers.
Exactly. But there's a catch there. Quantum computers are incredibly sensitive to noise and errors.
Oh.
The slightest disturbance can cause them to lose the delicate quantum information they need to function. It's like trying to build a house of cards on a vibrating table.
And that's where time crystals come in.
Potentially, yes. Remember that robustness we talked about?
Yeah.
Time crystals have a unique ability to resist disturbances thanks to their topological order. If we can figure out how to harness this property, it could lead to much more stable and reliable quantum computers.
So it's like building that house of cards with pieces that are somehow glued together. It can withstand more shaking without falling apart.
That's a great way to put it. Time crystals could be the key to overcoming one of the biggest challenges facing quantum computing. And that's just one potential application. We're really just at the beginning of exploring what these bizarre and beautiful quantum systems can do.
This is pretty mind-blowing. So what's next for time crystal research? What are the big questions scientists are trying to answer now?
There's a lot of exciting work happening right now. Some researchers are trying to create different types of time crystals, exploring new materials and arrangements of qubits. Others are investigating how to control and manipulate time crystals more precisely. with the goal of eventually using them to perform useful computations.
So we're still in the early stages of understanding and harnessing these time crystals. It's like we've discovered a new element, and now we're trying to figure out all the amazing things we can do with it.
Exactly. And who knows what the future holds? Maybe one day time crystals will be powering the quantum computers that help us solve some of humanity's greatest challenges.
Well, on that note of scientific optimism and infinite possibilities, I think it's time to wrap up this deep dive.
Yeah.
It's been an incredible journey exploring a topic that truly stretches the limits of our imagination.
It has been a pleasure.
And to you, dear listener, thank you for joining us on this adventure into the world of topologically ordered time crystals. If you want to learn more, we've included links to the original research and some additional resources in the show notes. Until next time, keep that sense of wonder alive, and we'll see you on the next deep dive. A shout out to our many listeners in Gibsons, Sechelt, Melbourne, Helsinki, New Orleans, Vancouver, Singapore, Copenhagen, and Sydney. We see you. Thank you for subscribing, following, commenting, and supporting our podcast. Find related articles at Heliox Podcasts on Substack.